Welcome to the ICID webinar on adaptive flood management, inundation forecast and mitigation. Am I audible? Okay. Yeah. Thank you. Thank you. So, welcome to the webinar on adaptive flood management, inundation forecast and mitigation, organized by ICID. The floods are a disaster which are having a very regular frequency of occurring somewhere in the world during most parts of the time. And now, given the increasing global concern over intensifying frequency and severity of the flood events due to climate change, this webinar will delve into the advanced methods and strategies for forecasting and mitigating floods in rural areas and farmland. The need for adaptive approaches that can respond to the evolving climatic conditions and unpredictable weather patterns is more pressing than ever. The traditional flood management techniques are proving inadequate in the face of these new challenges, underscoring the need for innovative solutions. The session will explore the science of inundation forecasting, latest technological advancements in flood protection prediction, and practical mitigation measures that can be implemented at local, regional, and global levels. By bringing together experts from various fields, we aim to foster a comprehensive understanding of the adaptive flood management and provide actionable insights to enhance resilience against the future flood risks. So with this brief introduction, let me welcome all the participants to this webinar. We have a very heartening response, and more than 130 participants are now part of this webinar. We have eminent speakers who are there for this webinar. We will enumerate the speakers now. Professor Philippe Gobersville, University of Côte d'Azur, France. He's a professor of hydroinformatics at Polytech Nice Sofia and the Graduate School of Engineering, University of Côte d'Azur, France, since 1997. He is an eminent hydraulic engineer in a French consulting company and also has been involved in the projects world over, especially Europe, Asia, Africa, and all the major parts of the world. He has initiated the Tianjin International Engineering Institute at Tianjin University, China, and he has served as French director of the school. He regularly advises on international institutions, public bodies, and he was one of the founders of Asian Water Council, promoting innovative solutions for water issues in Asia, and is presently a vice president of the Asian Water Council. He is also president of the International Association of Hydro, Environment, Engineering and Research IAHR Council since 2023, and he has been engaged at a national level with French Hydroelectric Society as a management board member, division chair, and initiative of SIM Hydro biannual conferences since 2010. He has a very varied and very rich experience, and we do hope that we will be hearing a very informative presentations from him. Next speaker will be Dr. Pyatida Ruganasamy from Chulalongkorn University of Thailand. She has been a faculty in the Department of Water Resources Engineering since 2011. And she is also in a committee of the ICID Academic Working Group and observer of ICID Working Group on Water Food Energy Nexus. This is a very important group and very important activity. Her research includes water security assessment, applications of satellite-based rainfall or flood simulations, reservoir operations and optimization, applications of remote sensing data for riverbank erosion in Mekong River Basin, water-related ecosystem and impacts of climate change in hydrological system. Her research team has included the Hydroinformatics Institute, Thailand, and International Center for Water Hazard and Risk Management. She comes with a very comprehensive water resources field management experience, which is quite relevant for the tropical countries like India and Thailand. The next speaker will be Dr. Bing Chen Zong from NSYSU, Taiwan. He is currently an assistant professor in the Department of Marine Environmental and Engineering at National University. His research includes the real-time forecasting of water-related disasters, artificial intelligence and machine learning, optimization algorithms and applications, climate risk assessment and adaptation, and spatial informatics. He has proposed a physics-informed inundation forecasting model that integrates artificial intelligence and multi-objective optimization analysis to analyze key factors and effectively improve the accuracy of forecasting model. So he is working basically at a very cutting edge of the technology that is there in the areas of artificial intelligence and machine learning, and he has proposed and applied a method that integrates climate adaptation algorithms and hydrological statistical analysis to the case studies in Taiwan and Japan. And his research in recent years has focused on real-time dynamic risk management of flood damage to crops during typhoons. He has integrated real-time inundation forecasting information, spatial distribution of crops, and vulnerability analysis to further quantify real-time dynamic risk and explore corresponding adaptation strategies. We will be having two moderators, Professor Ming Che Hu from National Taiwan University, Taiwan, and he is a professor in the Department of Bioenvironmental Systems Engineering at the National Taiwan University, and he works on the economic analysis models and software for water and energy system analysis and environmental planning. And he is currently serving as reviewer, guest editor, and editor members for several peer-reviewed journals. And he is a member of the working group on adaptive flood management and other groups of water, food, and energy nexus in ICID. And another moderator is Dr. Keigo Noda from University of Tokyo, Japan. He is an associate professor in the Department of Biological and Environmental Engineering, the University of Tokyo, Japan since 2023. He has more than 10 years experience in irrigation and drainage ecosystem services, water chair of the working group on institutional and organizational aspects of irrigation or drainage system management in the International Commission on Irrigation and Drainage. So we have got these two moderators and then these eminent speakers. So now I would now request for the opening remarks by the Vice President Honorary Dr. Kamran Imami, who is the chair of the working group of adaptive flood management. Yeah, so Dr. Kamran Imami, please.
दिखा दिया इसको हटा दो फिर ऑन कर दो शेयर स्क्रीन पर
Dr. Imami, you are on a mute.
मेरे को भी जो है होस्ट बना देना होस्ट
इनको अनम्यूट वो आई थिंक उनका अनम्यूट हो नहीं रहा है।
हाँ वो कह रहे हैं वेट करो जरा इसको वो कर देंगे अनम्यूट कर
हम यहाँ से नहीं कर सकते।
Thank you very much for the introduction. Thank you very much for the introduction. The working group on adaptive flood management was established in ICID in 2018, and it has published a journal paper on adaptive flood risk management, and we are planning to present a publication on adaptive flood management, and we can use all the materials presented in this workshop or other workshops or other webinars. I should like to be brief. The most important challenges of the flood engineering in the 20th century is designing and managing safe and economic water schemes in the view of uncertain design parameters. Uncertainty is the most important challenges of the flood engineer, and adaptive flood management is about coping with these uncertainties. And in this context, learning is very important. Hopefully, this webinar can help us prepare future publications and papers on adaptive flood management. Thank you very much.
Thank you, Dr. Imami. And then we will have the first presentation by Professor Philip. He will be making a presentation for about 15 minutes.
Thank you very much. I suppose I can start now. Is there any extra introduction from the moderator, or shall I go?
No, please go ahead.
Okay. Thank you very much, and very pleased to be with you this afternoon. So thank you for the invitation and for joining one of those webinars. I'm very happy to participate and to join this community. I will have a difficult task to do because, in fact, I will only partly answer to your question, but what I would like to do is to raise some of the challenges that are coming up with the new problems related with flooding and especially with extreme convective rainfall events. So this is a type of events that we are facing currently in different regions of the world. And what I would like to do in few slides is just to share with you first about the processes, but also regarding the potential impact and how we can try to cope with those elements. So just to start, I would like just to recall some of the data regarding some of the extreme events and their impact on the human society. What you have on the graph is just the evolution of natural disasters, natural hazard, and how they are affecting the human communities. And you have on the graph the magnitude of the losses. So this is a figure which is coming from a reinsurance company, so Munich Re in Germany. And so you see how those events are increasing and especially how they are serious since the last 20 years. If we try to move a little bit more within the details, this is what you have on this slide. You see the number of events that we are recording per year is continuously increasing, and especially the hydrological events or water-related events, meteorological events, are increasing. You see the magnitude of the blue and the green getting more and more higher and impacting quite strongly the human community. If we move to the details and if we look really to the hydrological events, so which is one of the most serious one, you see that we have around 400 major events per year affecting worldwide the communities and making a significant impact. And if we move to the last category, which is related to convective storms, this is the most recent data that have been published by Swiss Re, which is the other reinsurance company, very well known. You see that this impact related to those events is continuously increasing for reaching a value which is close to $70 billion per year. So which is something which is quite important and which is right now the most severe disaster affecting population in the world. So what are we talking about? So first of all, of course, if we are talking about extreme flooding, so we may have extreme rainfall and extreme runoff. And most of the time, this is related to very specific meteorological situation that can produce high intensity rainfall. Most of the time, it's above 70 millimeters per hour. Sometimes it's even much more higher. Some of the records, the recent records, were above 200 millimeters per hour. Those convective storms are frequently associated to stationary situations. So it means that the convective cells remain located at the same location for a while, and then they are pouring very significant quantity of water, which is generating a massive runoff. This is what we see around the Mediterranean Sea. This is some of the satellite images that we are recording over the Mediterranean Sea, but this is also conditions that have been observed in many countries and especially in Asia quite recently. What you have on the screen are a video and a picture of a convective cell. So it has a very small spatial extension. Sometimes it's below 5 square kilometers. It has a very fast development. Most of the time, those processes are not integrated within the meteorological models. So this is quite difficult to predict and to monitor. And it's obviously combining very high intensities. In the case of the Mediterranean situation, the situation is quite simple to understand. We have most of the time winds coming from the south, coming from the north part of Africa, crossing the Mediterranean Sea, being strongly, heavily loaded by humidity. And when this humidity is reaching the coastal mountains, it's generating massive runoff, as we can see in most of the time during the autumn period. So this is some of the pictures. You are maybe more familiar to see hurricane, typhoon in Asia and along the western coast of the Americas. But this is also something which is taking place over the Mediterranean Sea. You see over Sicily and Greece on the right, and a little bit more in the north coast of Africa on the left side. So those pictures have been recorded of recent events. And if we look on how many events we have seen, we see clearly an increase over the last decades. In a way, the recent years have not seen so many events, but during the past decade, we had more than 20 events every decade, so which is quite severe and was generating massive impact. So what is the main driver for this new type of situation? This is basically the increase of the temperature of the sea, and especially at the autumn season. During this period, we have a temperature anomaly for the sea surface, which is frequently reaching 24 degrees. And when we have those 24 degrees combined with the south wind coming from the north part of Africa, we have the possibility to generate such a type of event, which are most of the time located at the end of September or at the first half of the month of October. And this is what we are observing over the last 15 years. So in most of the cases, we are facing in those situations a quite very intense runoff. And of course, this intense runoff cannot be managed within the cities. The intensity, the quantity of water is just too high for most of the drainage systems that have been designed, just because the quantity is too big. And obviously, we do not have the financial capacity to invest for structures that can totally defend and establish a flood-proof city environment. So in that case, we cannot be a flood-free situation. And of course, this is very difficult for the managing team, but also for the population. At the same time, we have to face the evolution of the urban environment. The city is growing. We have a spatial extension. We have more and more impervious surfaces, which are linked to the development of the urban growth. And of course, at the same time, we have an increased vulnerability of those new infrastructures. So it means we have to develop alternative solutions for preserving services, preserving functions, urban functions, but also the surrounding of those cities to be sure that they can potentially react properly in case of those type of extreme situations. I would like to take two examples and try to elaborate a little bit on those situations. The first one took place in October 2015. It was one first convective event that was affecting the coast in France along the French Riviera. The quantity of rain received was about 260 millimeters in 2.5 hours, so which is quite short. And we had a quite severe number of victims because 21 people were dying. The total of direct damages was above 1 billion euro. And you see some of the pictures on the slide regarding this situation that was happening during one event. On the video, you see how intense was the rain, sufficiently intense to stop a football match, and to ask the participants and to be the spectators of the stadium to evacuate this stadium and to move back home. It was maybe not the most clever decision because it was pushing people on the road and creating traffic jam and bring people exposed to the risk of flooding. But it was quite imprevious situation. If we look at the map, you see the lighting activity on the right, and you see how the cell was traveling along the coast and was almost stable for 2.5 hours and generating massive precipitation over the area. You see the distribution along the different municipalities was close to 200 millimeters, and almost half of that only in few kilometers distance. So it means that the spatial variability is extremely high. So it means the design of protection measures is quite difficult to achieve if we do not know in advance how this water can be distributed and how we can react. Even if Nice is one of the most greenest city in France, you see the coverage with trees and alternative solution is quite important within the city. We had such a type of situation. So you see the water flowing within the street and population or citizens just crossing the streets and taking risk to be washed away by the water, which is a little bit dangerous and a bad behavior. Consequences have been quite impressive. What you see over there is just the entrance of the station. So several trains were blocked within the station with public inside. So it was adding an additional crisis. Just to say, this type of event was in fact not really new. What is new is the intensity and the frequency that has increased, but it has been already recorded in the past within the region. You have some pictures of a similar event that was recorded almost 1 century ago, and that was affecting a village, of course, with much more limited consequences compared to the situation that we have recorded in 2015. If we look at the intensity, nothing was really exceptional. You see that we have already recorded events more than 180 millimeters per hour in the past. But what was new was the extension and the spatial dimension of the rainfall that was generating the things. One of the difficulties regarding the impact was, in fact, the communication to the public that was not optimal at that time, because only a warning signal or warning issue was provided to the population, which was not the most highest one compared to what we can do. It was only a range information that was provided in this region because the model were not just sufficiently accurate to forecast properly 24 hours what could be the things. We were able to simulate and to model properly the event, but the results was coming just the day after. So it means in 2015, we were not able to do sufficiently accurately. I would like now just to cover another example that took place 5 years later, almost at the same date, 2nd of October. In that case, we had a much more intense rainfall event, which was not located along the coast, but a little bit more upstream. We had more than 500 millimeters. I say more than 500 millimeters because most of the devices installed on the field were not able to register properly the information. We know that most of the threshold were exceeded, even for the radar devices that were used. In that case, we had hopefully only 9 people who died, but with damages 1.5 billion euros. The situation was affecting this nice village in the upstream part of the catchment, in the upstream area of Nice. And we had a quite massive runoff. You have an idea on this video about the flow of this river, which was less than 2 cubic meters few minutes before that. And that was deeply affecting the valley. We had massive destruction, massive erosion. You can see on the pictures how far the river was enlarged and attacking and destroying structures. That's the case for the houses, but also destroying some historical houses that were never affected by flooding before. Even new construction, new irrigation installation were also destroyed, and several hydraulic structures were deeply affected. In this case, we had a very unique situation because we had not one stationary convective cell, but we had 3 convective cells at the same time. You see on the map the 3 elements being there for almost 6 hours and pouring more than 500 millimeters. It was the first time that this type of event was recorded in Europe. So this is something which is new and that has to be seriously being taken into account. You have the spatial extension for this situation, which is showing how it was covering the catchments. In such a case, consequences were a little bit more limited than what we had previously for different reasons. First, because population was in some extent prepared due to the recent flooding, and also because the warning procedure was more efficient. We had, in fact, a better forecast, and the day before, we were able to produce those maps saying that potentially an extreme rainfall exceeding 300 millimeters will be affecting the catchment. And so the warning issue was much more accurate and much more efficient to the population. So in fact, 6 hours before the flood itself, a red signal, a red alert was provided to the population asking everyone to go to a shelter or to stay in a safe place in order to minimize the consequences. The plan was operating well. You see the same map as for 2015, and you see the red area, which was in fact on time produced for this region, allowing to preserve the population and to have the safeguarding procedures being properly implemented. So one of the lessons of these 2 things is that right now, if we want to cope with such a type of event, we need to simulate the unexpected. Following these events, the different guidelines have been reviewed regarding the design, not to make wider structures regarding the protection, but just to take into account such a type of situation. What if a similar event is happening? How we can anticipate, how we can increase the resilience of the environment, resilience of the structures, resilience of the population regarding such a type of things. One of the key tools for moving forward, and this is what we have seen, is to use deterministic model to try to estimate extreme situation. We have now one system operating continuously and simulating the water cycle. The objective of this tool is to simulate the different aspects of the water resources, but also the extreme condition. And as you can see, for the situation of 2021, it was possible to re-simulate properly the condition and to have a good idea on what was the magnitude of the things, due to the fact that most of the devices on the field were destroyed by the event itself. What was very impressive was to quantify the runoff coefficient for these extreme events, and we had more than 79% of runoff being recorded on the field. So it means even if it were pure rural places, the actual runoff was extremely high. So we were able to reconstitute the different hydrograph and to propose a simulation. We published quite recently, 1.5 years ago, some of the results comparing the added value of deterministic models compared to the different stochastic or data-driven models. And we can see clearly that we had a very consistent and very significant quality within our results. So this is the final hydrograph that was produced. It was sufficient to support the rescue team to operate and to engage rescue services on the field. Today, those data are used for designing the things. Some of the comments and observation. Convective rainfall events are for sure exceptional, but they are apparently increasing in the recent years. Due to the extreme intensity they are introducing, they are generating massive runoff where we do not have the capacity to cope with. So it means we have to integrate the fact that the flooding will come, whatever we do. but we need to minimize consequences by increasing the resilience of the different environments and to improve the communication procedures. I would like just for conclude, just to show you another example that took place recently in 2021 in July in Henan province in Zhengzhou city. We had more than 200 millimeters per hour, and this is a quite serious intensity, as you can see, with quite severe impact within the urban environment for the public transport and of course for the drainage system that has never been designed for such a type of things. So that was some of the key messages. I think it's important to understand that we cannot produce flood-safe environments, so we should be prepared, especially for those extreme things. I'm not advocating for making bigger infrastructures, but I'm just mentioning that we need to improve resilience by being more aware about consequences of those type of situations. As a conclusion, I would like to invite everyone to visit our flash flood website. So we have one ongoing activity on those type of events in different regions and especially in Asia. So it's totally free. So if you are interested, you can go on this website and you can have more webinars, more information and documents that could be shared and circulated on this type of events. With that, I would like just to thank you very much for your attention, and I'm ready to answer to any questions that could come up afterwards during the Q&A session. Thank you very much.
Thank you, Professor Philip. It was a good, very interesting presentation. And we will take all the questions at the end of the webinar. So all participants are requested to put their questions and answers in the Q&A box, and we will try to moderators will try to help them answer the questions. Next presentation will be by Professor Keigo Noda, Japan. He is also a moderator, and we will give the floor to Dr. Keigo Noda.
Okay,
Yes, we can see your slides. Yes, we can see your slides.
Okay,
So welcome, President.
Thank you for introducing me. It's a big honor for me to have a presentation at this webinar. Today, I'd like to introduce Japanese governmental activity for basin level flood mitigation measures by using paddy fields and irrigation systems. I'm Keigo Noda from the University of Tokyo. I'm working for INEP Japan Committee as well. Now, this is the introduction. In order to address intensified and frequently occurring flood disasters caused by climate change in recent years, efforts of all stakeholders in basin areas are required to progressively promote basin flood control. At low-lying areas in major river basins in Japan, paddy fields are widely stretched to the suburbs of cities and residential areas, as well as upstream of the basins. A lot of irrigation dams, ponds, and drainage facilities are also located in the basins. So actions to use the multifunctionality of these facilities and paddy fields are needed to contribute to achieve the basin flood control. We have 4 initiatives to promote the basin flood control, from improvement to management of irrigation facilities. After this, I will introduce one by one. The first initiative is utilizing drainage facilities, and the second one is utilizing irrigation dams. The third one is utilizing irrigation ponds, and finally, number 4 is utilizing paddy field dams. This illustration shows the locations in the basins of each initiatives are conducted. The first initiative is utilizing drainage facilities, but disasters are increasing in recent years because of insufficient function of irrigation drainage facilities. Such a functional deterioration is caused by the change in flood pattern due to urbanization. MAF has started a 3-year emergency program to rehabilitate drainage pump stations and drainage canals, which will reduce damaged areas in the future and the cost of damage under heavy rain. The bottom show the example of improvement of drainage function and Yoneda pump station. To gain the adequate drainage capacity of the Yoneda area, rehabilitation of the Yoneda pump station was implemented under the 3-year emergency program. Together with the improvement of drainage canal by another project, the drainage capacity in the area has been increased from 3.67 cubic meter per second to 4.5. The second initiative is utilizing irrigation dams. Considering the increase in intensified flood disasters, MAF has started a measure to discharge reserve water at 414 irrigation dams in 2020 to strengthen the flood mitigation function. When the typhoon number 14 arrived in September 2022, 70 MCM of flood mitigation capacity was generated at the 62 dams, among which the Kihok Dam in Kagoshima Prefecture generated 0.42 MCM. The left bottom picture shows how to strengthen flood mitigation function of dams. Flood mitigation capacity of dam is strengthened by discharging reserved water 3 days before the heavy rain is expected based on the water forecast. The right bottom hydrograph shows how it works in the case of Kihok Dam in Kagoshima in 2022. The green line showed inflow and red line was actual discharge. As you can see, the flood mitigation capacity 0.42 MCM was generated before the heavy rain comes, and the discharge peak was cut by this capacity. The third initiative is utilizing irrigation ponds. Agricultural ponds have a multifunctionality to mitigate flood damages against farmland in downstream areas by storing rainfall water in the ponds. Installation of a slit at the spillway is one of the easiest measures to increase flood mitigation capacity of the ponds. And those figures show the case studies in Asakawa ponds. You can see a slit at the spillway of Asakawa pond. This slit lowers the water level without any additional operation. The last initiative is utilizing paddy-filled dams. Paddy-filled dams is a measure to reduce the flood risk at the downstream and neighboring areas. By setting a wear plate or adjustment board with a hole at the drain pit to delay the discharge from paddy fields, rainfall water is temporarily stored at paddy field dam and gradually discharged to drainage canal so that rapid decrease in water level at the drainage canal and downstream rivers can be avoided. The left bottom pictures show the effectiveness of paddy-filled dam. The left hand shows with paddy-filled dam, and if the paddy field dam is not in study. The right picture shows the drainage canal is flooded. Those 4 initiatives still have some requirements or preparation. For example, in number 1, utilizing drainage facilities, the repair enhancement of pump capacity drainage operation before rainfall are required to strengthen this function. And for the second initiative, utilizing irrigation dams, repair sediment removal in the dam and capacity building for gate operations are required. And for the third initiative, utilizing irrigation ponds, reinforcement of embankment, improvement of spillways, avoid to O&M organizations are required or expected. And for the fourth initiative, utilizing paddy field dams to develop drainage facility to install a wear play cooperation of farmers in the area are required and expected. Okay, this is the end of my presentation. Thank you for attention. For more information, please visit MAF's website or contact with me personally. Thank you very much.
Thank you, Professor Keigo Noda. You presented some interesting concepts of utilizing the irrigation ponds for flood moderation. Now we will be having presentation by Professor Piatida Runga Sami from Thailand.
Good evening. Thank you very much for the introduction. I will share my slides. It is my great honor to join the webinar by ICID today. The topic of my presentation is the operational rainfall runoff modeling system with the application of satellite-based rainfall for the Chao Phraya River Basin in Thailand. I'm also the committee of the Thai CID Academic Working Group and member of ICID Working Group on the Water, Food, Energy Nexus. And before I begin my presentation on the flood, I would like to share a little bit about our seminar in Thailand that's happening on this Wednesday, this coming Wednesday, July 3rd. It's the 17th ICID National Symposium. And this year we are very honored to have the president of ICID joining us in Bangkok on the topic of the adaptation of ICID to cope with global uncertainty and extreme climate. A great event from Thailand. And today I will be sharing about the collaborative project that we are working with the Thai agency and also the collaboration with ICHAM on the operational rainfall runoff modeling system and the forecasting system. So this is the overview of the 12 system that the Hydroinformatics Institute in Thailand have developed, ranging from the atmosphere to the ocean, including the using the remote sensing weather radar, telemetering station, and several models. And we contribute in the development of the rainfall runoff modeling system. So this collaborative project is with the Hydroinformatics Institute in Thailand with the support from the Ministry of Higher Education, Science, Research and Innovation and Chulalongkorn University as well as ICHAM. So we completed the first phase in 2023, developing the modeling system for the Greater Chao Phraya River Basin, Chi River Basin, and Moon River Basin, and we are beginning the second phase this year until next year. So this is the flood the big flood in Thailand in 2011, and this is the one of the top 10 costliest disaster. And I put the word natural in the quotation mark because this is not only from the heavy rainfall but also linked with the operation and management. So for Thailand flood warning system, we have the monitoring, early warning, evacuation plan, and also recovery. So it involves several government agencies, for example, the Thai Meteorological Department, Royal Irrigation Department, Department of Water Resources, and now we have the Office of the National Water Resources, as well as the Department of the Disaster Mitigation and Prevention and Mitigation, and also Department of Mineral Resources that are involved in the process. So the project that we've been involved, the objective is that we develop the distributed rainfall runoff modeling system. And after finishing the second phase, we will develop the modeling system for the whole Thailand, for all 22 river basins in Thailand. And we will do the calibration and verification. And we also apply the bias corrected iMerge product for both flood and drought analysis. So this system will be part of the HII Earth observation that will support the big system for Thailand. And also we will develop the forecasting system. And this operational system is an automatic system with the database in standard format that link with the decision support system of HII. And the model that we developed is based on the rainfall runoff inundation model developed by iCharm. And this is the input. We need the rainfall, DEM land cover cross section, and we have the main output on the discharge water level inundation. So the RI model is distributed model with the 1D diffusion in river, 2D diffusion in catchment. And this is the map of Thailand, and during 2022 and 2023, we developed and calibrate and validate the model in the Greater Chao Phraya River Basin, as well as the Shi River Basin and the Moon River Basin. And in the next phase, we will develop for the other river basins. Yeah. So to give you more idea of the scale that we are dealing with right now. So for the Greater Chao Phraya River Basin, the entire area is very large, about 160,000 square kilometers. And it consists of several basins from the north, which is the mountainous region, to the floodplain area. And you can see from this picture that in this area, this is the large irrigated area of Thailand, and we grow rice in this area. And we have a lot of the irrigation infrastructure in this area. So the flood forecasting is very challenging because it involves the management and operation of the infrastructure as well. So our objective is try to focus on the unregulated flow first, but we incorporate the reservoirs into the model as well, and we use the release from the reservoir as the boundary condition. And these are the data that we obtained and used in the model. For example, the topography in the Greater Chao Phraya River Basin, we use the Merit Hydro with the resolution of 1 kilometer by 1 kilometer. And then for the rainfall, we use the observed rainfall and satellite-based rainfall. And for the land use, we classify into 5 types, including forest, crops, agriculture, urban, and water body. And we use the cross-section from Royal Irrigation Department, the release from Electricity Generating Authority of Thailand, and we use the satellite image as well for the comparison of the inundation area. So I would like to share that the rain gauge network in Thailand is quite dense. So we have the rain gauge from the Thai Meteorological Department for T-hourly data, and the rain gauge from the Hydroinformatics Institute for hourly data. And this is the distribution of the rain gauge network in all the region in Thailand. And this is the another work that we've been involved is the application of the satellite products. So we used GS map, Persian CCS, and also iMerge with different spatial resolution, and we apply the bias correction method, including the quantile mapping, linear scaling, machine learning using random forest and autoencoder. So these products are used for both flood and drought. And this is to share some of the performance of the autoencoder and random forest. So this is the heavy rainfall event during January in 2019, and the dashed line is the observed rainfall right here. And we use the iMerge early run and iMerge final run. So the green line here show the bias corrected iMerge with the autoencoder. So we can see that compared to the original iMerge, which is the blue line, we can get the bias corrected image rainfall to be closer to the observed. And when we develop the model, this is the calibration and validation, and this is the work that focusing on the calibration using the data in 2011. This is in Nan River Basin, Yom River Basin, Wang River Basin, and at the control station right here, which is the beginning of the Chao Phraya River. So this is important station for us for the lower Chao Phraya area, and Bangkok is around here. And this is the comparison of the simulated inundated area with the satellite image from GISDA. This is the flood in 2017, where we also have a lot of rainfall. The EOD is about 63%, and fall around rate is about 23%. And right now, the operational system consists of 3 parts. So we have the preprocessor to preprocess the input data for the RI model, and then the simulation system and the post-process for the output. And for the daily simulation, the system runs at 12 p.m. And we also have another part, which is the monthly simulation. The purpose of the monthly simulation is to identify the appropriate parameter set because we have developed a parameter set for normal condition and for extreme condition, which is wet or dry year as well. So these are the example of the gridded or map. So we can visualize the water level in river, inundation level, and also river discharge. And for the next step, we will incorporate the forecast rainfall from HII, from the Hydro Informatics Institute. This is the example of the forecast rainfall today with the initial date yesterday at 7 p.m. Bangkok time. So the forecasted rainfall product from HII includes 3 products. The first one is the forecast 3 days in advance with the resolution 3 by 3 kilometers. And the second product is the 1 to 7 day forecast covering Southeast Asia with a resolution 9 by 9 kilometers. And the third product is the forecast 1 to 7 days in advance covering Asia with the larger resolution of 27 by 27 kilometers. And we are looking forward to improving our system. So we have developed a modeling system, and then in process, we are trying to develop for the other river basin and also incorporating the forecasted rainfall. And then for the future work, we would like to incorporate data simulation into the system. And for my talk today, I share the operational and automatic system of the distributed rainfall runoff simulation with the database that link with the decision support system. And for the next step, we will develop the forecasting system based on the established distributed rainfall runoff modeling system and forecasted rainfall, and importantly, the system for the information dissemination. So I talk a lot about the modeling system because you know, we can do a lot of analysis and the scenario analysis and forecasting. However, there are also a lot of limitations in terms of the modeling with the uncertainty, the false alarm, and also we need to use a lot of resources. And our challenge is on the accuracy and timeliness of the warning and also for the mitigation. Thank you very much.
Thank you very much, Professor Piyatida. This was a very nice presentation. We had a very good glimpse of how the simulation models can be developed and run. Now we will have a presentation by Professor Bing Chen Zong from Taiwan.
Okay, hello everyone. Supposedly you can hear my voice, so now I'm playing my slides here. Okay, so ladies and gentlemen, and Professor Minze Hu, and all the professors here and participants in this session, good afternoon, good evening. My name is Bing Chen Zong. Thank you very much for having me here so that I can share with you the preliminary result of my current study. So about the study, what I'm going to share with you today is, the title is Real-Time Risk Assessment based on typhoon-induced inundation forecasts. Today, I just want to try to focus on the one case study of the paddy fields, okay? So in the beginning, I'll try to briefly introduce you the study, methodology, application, results, and discussions. And finally, we will land on conclusion. Okay, so just as we know, when heavy rainfall events occur, or you can say storm event occur, human beings, people, we have to suffer from several different disasters, such as like the flooding and inundation, right? And in addition, you can also see the pictures from these slides. A lot of buildings, infrastructures, and land resources were also inundated under the water, right? Which includes agricultural crops, such as like the paddy field. So actually, warning system is very important, just like the several professors they have already mentioned before, okay? So why? Because it can increase the mitigation time, and it can help decision makers to make a emergency notification. Okay, so traditionally, you can also see that two-dimensional numerical models have already been extensively used for the simulation of complex physical processes underlying flood dynamics. Okay, so for example, we can use DEM data, design hydrograph and rainfall data, and so on, put them into the numerical model, right? We try to use a mathematical equations and so on to try to appropriately simulate the physical phenomena by using computer. Okay. However, the aforementioned methods have several limitations, such as like their high computational and data storage requirements for inundation database preparation and management. However, here we have one assumption. The assumption is that if you want to focus on the issue of real-time inundation forecasting, if you want to do that, okay, and you also want to use a complex model to try to forecast an inundation depths, I would say it might be relatively difficult. So in other words, if we can have a modeling method with a low computational load, it would be better, right? And it should be developed to overcome the technical challenges, just like what I mentioned. Okay, so everybody, just like what you see here, recently, especially in the recent several years, artificial intelligence, AI, machine learning, and deep learning approaches that they have already been paid attention, right? Okay, so why they have already been paid attention? Because you can see they can effectively capture the complex, nonlinear relationships between input and output, right? Okay, so we can say this way. Excuse me, those approaches, they are alternatives to numerical models, not just try to replace them, okay? However, especially for some study area or some places, if they don't have sufficient historical observation data of inundation depths, maybe this is another good idea. We can integrate numerical models and machine learning approaches. For example, we can just try to apply inundation database simulated by numerical models to further train and test the real-time inundation forecasting models developed by machine learning approaches or something like this. This is a kind of idea. However, everybody, did you notice that about the topic of climate change? And I know this is another different issue, but it's happening, right? Recently, climate changes have had widespread impacts on human and natural systems. And you can also see that climate change is one of the important factors affecting spatial and temporal patterns of precipitation, and intensifying precipitation and the hydrological cycle, right? Just like the former presenters, they have mentioned a lot of these kind of things. So in my opinion, I just an idea just came up with my mind one day. So in addition to only focusing on inundation forecasting, flood forecasting, is it possible to additionally increase to consider to increase how can I say the core concept of the climate risk into the flood early warning system? Is it possible? So based on this kind of idea, we can see, we can just try to review IPCC AFI report that have already clearly defined the climate risk, right? So you can see the climate risk just from this picture on these slides. It consists of the three components, okay? So for example, hazards, exposure, and vulnerability, okay? So another different idea is also based on that kind of concept, is it possible to propose a comprehensive framework for assessing real-time inundation dynamic risks to investigate cause of risk resulting from climatic and non-climatic factors, or we can help people to take or to have a risk communication based on this architecture and so on. Okay, so in this study, I try to propose a generalized approach of assessing real-time inundation dynamics risks for petty fields, because this is a case study in this research, right, today. So during typhoons, so based on the component, just like what I mentioned, hazard, exposure, and vulnerability. So hazard in this part, it is based on the integrating, we can focus on that, integrating a numerical model and AI-based approaches. So in other words, real-time inundation forecast, this kind of information can be seen as the hazard, right? So exposure and vulnerability can be additionally considered. For example, predicted target, what kind of target you want to protect. In this case, I want to talk about petty fields. So the petty field will be the target. And we can further to discuss about the vulnerability factors of the predicted target, or something like this. So this is the proposed approach in this study. Actually, I have the 4 steps here. The first one is just what I mentioned, right? I used a numerical model to try to obtain the simulation of inundation database. And in step number 2, we can develop a real-time inundation forecasting model by using AI-based approaches with a feature engineering. And in the third step here, this is a new algorithm. I know, yeah, just let me mention about that, which is called climate adaptation algorithm. I will mention that later clearly. So maybe we can use this algorithm as a tool to do qualitative analysis. For example, we can analyze potential factors in the form, or you can say in the tool, okay? And in the step number 4, based on the result of the qualitative analysis, right? And then is it possible to do the quantitative analysis to show the different risk levels and to further show the risk maps to let the decision maker, they can consider, they can see, they can think. So in the step number 1, the numerical model, what I used here is SOBAC model. So it actually includes several different modules, just like a rainfall runoff module, the flood plain, the overland flow modules, and so on. And step number 2, the forecasting model, what I used here, actually I used 2 algorithms. The first one is a support vector machine, we call that SVM. The other one is multi-objective genetic algorithm, we call that MOGA. So I try to combine both of them here. So let me call that as SVM, MOGA. Okay, so I have the 3 blocks here. At your left-hand side here, first of all, we have to determine the input data, right, and the parameters. And the second of all, we can implement the procedure and the process of the algorithm. And at your right-hand side here, this is the final block, and we can have we can obtain the optimal input combination, and we can also check about the model performance, or you can say model accuracy. And in the step number 3, the algorithm what I used is a climate adaptation algorithm. Actually, it includes two parts. The first one is climate change adaptation 6 steps at your left-hand side here. And the other one I want to mention, the one tool that I want to mention more is the other one, which is called the Climate Risk Template, CRT, just like picture what you see at your right-hand side. So for example, you will see by using this template, you can see, oh, what is your governance level? What is your stakeholders? What kind of key issue they concerned? And what kind of target that you want to protect, right? And based on the core concept of the climate risk defined by IPCC 5, so we can, based on hazard, exposure, and vulnerability, to further discuss climatic and non-climatic factors, adaptation, capacity, and sensitivities, and so on. Sure. So in the final step here, this is a spatial risk assessment. They're very easy. At your right-hand side, we have the two figures, right? If we can quantify the level of exposure and vulnerability, and then we can further to use the risk assessment metrics to additionally consider the level of hazard. And then we can further to determine about the level of the climate risk. For example, the red one, severe, significant, moderate, and so on. Okay, about the application, this is my study area. That is Yilan County. And you just like the picture at your right-hand side. What you see here, Yilan County is located near the northeastern part of Taiwan, right? Okay, so here in this case study, I used 16 rain gauges and 5 type of events here. And also you can see several yellow points here. There are 9 sites. They are chosen as the inundation reference points. So this is the inundation database simulated by SOBEC model, okay? So I just try to use the 2 typhoon events, Meiji and Saola in 2010, 2012 respectively for calibration. The other one is Typhoon Parma in 2009 for validation. So you can see the result. We can say the result will be appropriately simulated by SOBEC model, okay? So we try to further use the inundation database to go to develop the real-time inundation forecasting model. And in this case, I just try to use different algorithms with the same input combination in the first step because I want to compare the model accuracy. For example, BPN, MFIS, SVM, MOGA, just like the proposed approach what I mentioned earlier. Oh, okay. So you can see the model name BPN1, MFIS1, which means that the number means that the same input combination. And in the second step, that I want to talk about the benefit of the using different inputs. So I changed my strategy, right? I just try to use the same algorithms here, but you can see the algorithm, the number with the different numbers, 1, 2, 3. That means that I just try to use a different input combination. But however, everybody, I know we have the time constraints. So it is almost impossible to show you everything, every result in this very short 15 minutes here. It's pity, but I'll try my best to share with you. So please allow me to share with you about the potential factor analyzed result by climate risk template. So I just try to operate that by using this tool. So you can see the result just like this. So the governments, Yilan County local government and stakeholders, they can talk about the key issue, right? For example, the target is petty fields. So they can talk about the climatic and non-climatic factors, and all of them, they are related to they are related to the inputs and parameters of the SOBEC model, right? Because we can use climatic factors and non-climatic factors to try to simulate the inundation depths. Okay, and second of all, you can also see that the blue regions here, guys. So for example, the exposure, I use the spatial distribution of petty field. It's not very difficult, but the more interesting thing is adaptation capacity, right? We can discuss about the petty field, their adaptation capacity here, and the sensitivity of the petty field. For example, rice varieties and the rice plants height, they are related. They can be affected by the inundation depths as well. However, it is worthy to mention, the things is it is worthy to mention here is the government, about the adaptation capacities of the government. I think the governments, they also can be do something. They should be able to do something, right? For paddy fields or for farmers here. So, oh, I'm sorry. So you can also see that by using climate risk templates, and then we can try to list, or you can say we can try to investigate out of the adaptation options and all of the factors in the template, or something like this. Okay. However, because I'm still in my progress, my study progress, so today I just show you the result combined hazard and exposure. In the future, I will just keep going to finish the vulnerability factors about the qualitative or quantitative analysis and the risk maps. Okay. So, for example, the left-hand side of the picture, the picture, this is a simulation by SOPEC model. At your right-hand side, this is a T+1 to T+3. So I call that this is short lead time forecasting. And this is a long lead time forecasting for the typhoon Sinlake in 2008. So you can see, okay, if we go back here, you can see the inundation the depth is not very high. It's just like a middle. But however, the model is inside the forecasting model actually underestimated, very obvious. However, if we focus on another different typhoon, for example, this one, Typhoon Saola in 2012. So at your left-hand side, this one, okay, everybody, you can see the simulation. The inundation depth, it was higher than the former one, However, for the AI real-time forecasting models, the performance, you can see about the short lead time and the long lead time. The pictures, the results, they're very similar to the picture, the result we see at your left-hand side here. So what does it mean? Now that means that even though the model, forecasting model, still slightly underestimated, right? However, it can maintain the level of the model to maintain the model accuracy. Okay, so let me do this conclusion. I know time's almost up. So based on the real-time hourly inundation forecast, is it possible to assess the dynamic risk? It seems that it is possible, right? It is possible by using the climate risk template. So if we use a CRT, the tool here, then we can talk about more potential factors with people, with the different parties, okay, with the different the people, and also we can further to discuss more clearly, discuss about the adaptation measures. So I hope the proposed approach is expected to be useful for agricultural disaster management, okay? So this is my future perspective, and thank you very much for your listening. And my name is Bin-Chen Zhong. Thank you very much again.
Thank you, Professor Bin-Chen Zhong. Very interesting presentation and a very erudite one. Now we have a brief time for the discussions of the participants. There have been many questions that have been raised. I would request the presenters to have a look at those Q&A panel and find the questions which are of relevance to them. And before we open up the Q&A session, we have President Honorary Raghav with us in the panel, and I would request him to make a brief intervention for 5 minutes.
Thank you, Secretary General. I would like to thank all the speakers. Very excellent presentations and very topical, really, issues that we are all struggling with. I have been myself involved in similar work. And the last project, I was looking at the extreme events of drought in the UK. The other thing is that we also have another issue here in the UK, is the seawater rise and inundation of coastal lowland areas. And that's maybe something that we should have another webinar similar to this one, to look at the sea water rise and the inundation of coastal areas and the impact on marshlands and also the farming along the coastal side. The thing also I faced is that the early warning system is not early enough. That's what I was told by so many people here in the community, that they don't get enough notice to evacuate and to prepare to leave their homes and to take their belongings and so on. So I wonder if there are some thoughts from the panel on how can we improve the early warning system really to be early enough to warn people to evacuate. That's one thing. The other thing also I faced and you are facing is the inaccuracy and the uncertainty in the data provided by climate change models. In my last runs of models, I had to run hundreds of scenarios that comes from the Hadley Center. I'm sure that you are aware of the UK Hadley Center that provides climate change models. And I had to run hundreds of these actually variations of the scenarios and also to run uncertainty analysis, because simply the British government cannot accept our results without having uncertainty analysis and confidence bounds to the results. So one issue really for that work that you are doing and I'm also doing is how can we reduce uncertainty? How can we make the early warning system to be early enough so we can do and help the community to move forward? The other thing is that we should maybe consider also the seawater inundation, not only inland inundation, because it is also important for people living on islands like the UK. And that's also an important issue to deal with, because simply I was told that inland inundation, it is a lot easier to cope with through reservoirs, through harvesting water into a lot of water storage capacities. But when it comes to seawater inundation, it's very limited, really, solutions available for the community. So this is just something for discussion. I thank you very much. Excellent presentation. I'm really grateful that I was able to attend and to listen and to learn from all your presentation. Thank you very much.
Thank you, President Ronald Raghav. And now we will open up the question and answer sessions. Moderators may take up the moderation for this question and answers. I would request all the questions to be brief, and then also matched by the brief answers. The detailed answers can probably be followed by the mail exchange between the participant and the presenter. So so there are questions, and few people have raised their hands. So we'll try to see if we can accommodate them. But in the meanwhile, questions can be taken up. So going in the sequence, Professor Philip, if you would like to answer some of the questions, maybe 2 or 3 questions, and then we can move to the next one.
Okay, I can try. From what I have seen in the chat box, it's a little bit confused. I mean, there is a lot of comments and it's a little bit mixed up. So, but I saw a question which is regarding accuracy, and this is coming up also to what has been said. Can we trust the forecast, and what do we need to improve the situation for having our forecast more accurate and being more efficient for the population? I think one of the challenges for the meteorological services, they need to provide more accurate forecasts for producing afterwards the hydrological simulation that we need to do. We do not have any big problem on the hydrological simulation, but the challenge is to have accurate meteorological forecast. And so this is one of the key challenge. And of course, we need to have that with a reasonable time. So at least for the processes I was describing, 24 hours ahead would be strongly needed. So being able to represent and to include convective events would be very challenging, and obviously it will be not for this generation of models, but it would be for the next generation. Apparently, we have seen progress. As I was mentioning in my presentation, over the last 8 years, which are quite positive. We have seen the capacity of communities to react, but the difficulty is really to provide the right information on time. And I think this is one of the key challenges.
Professor Keigo Noda, if you have any questions identified for you from the Q&A box,
yeah, I've already answered to the chat to all the questions.
Okay.
Thank you.
Okay, thank you very much. In a very efficient way of course, handling, because we have a very large audience of 163 or so. Then Professor Piyatida, would you like to answer some of the questions?
Yes, thank you very much. So there's a question regarding the implementation of RI model for mountainous area. And my answer is yes, because the RI model is developed in Japan, and the topography in Japan is very mountainous, and that's also the effort to running the RI model for smaller area with a higher resolution. And we also apply that in the industrial area in Thailand for the business contingency management. So we try to do the scenario analysis. And to resonate with Professor Philip, I think for the local community, it's very important for the community to understand the context of the area and understanding for the risk in the area. And we have a lot of good examples in Thailand for community-based management that government agency work with local administration and also with the community to prepare and to provide support before, during, and after the flood or drought. Thank you very much.
Thank you, Professor Piyatida. And now Professor Bing-Chen Zong, if you would like to answer some questions.
Thank you, Engineer Pandya. I just check about the Q&A section, the box. A lot of people asking me, may I share my presentation slides? I think it is okay. And I have already sent my slides to the executive director. So I don't know if the ICID here there. Did you have any way to share the slides to everybody?
Yeah, we will put our webinar proceedings on our website, and there your slides will also be available for the people to see.
Thank you.
Other presenters, if they agree, they can share their presentation with us so that we can also upload the slide along with the recording for the benefit of the attendees.
Okay, thank you for your answer.
And there are some questions in the question Q&A box. One question is from anonymous attendee. The anonymous attendee has raised number of questions, so I will not cover all the questions. I'll take just few questions. How accurate is the inundation extent generated by the RRI model? Please unmute yourself. Yeah.
May I quickly
Yeah.
share the screen? Yeah.
Yeah, it is sharing the screen.
Yeah. In terms of the simulated inundation extent is still quite challenging for us. So this is the comparison between simulation, which is the red area, and the satellite image, the blue area, and the intersect between simulation and satellite, which is the green area. So we still missing the inundation extent around the transition area, but for the downstream, we also simulate more than the satellite image. And this comes from several factors. For example, as I mentioned, this area is irrigated area, so that's a lot of operation and infrastructure. So in the model to incorporate the water management, water allocation and diversion is still quite challenging for us. Yeah.
Another similar question to you is whether this model can be used for mountainous areas also.
Yes, it's good for mountainous area.
Okay. Then Mr. Mohammad Hafiz Hassan has raised a hand. We'll give him the rights so that he can raise his question. Mr. Mohammad Hafiz Hassan. Hand raise किया ना उसको दे दो अनम्यूट कर ऊपर ही होगा सबसे ऊपर सब स्टॉप कर दो ऊपर टॉप हैंड रेज किया हो अनम्यूट कर
चेक करिए नहीं
अनम्यूट कर अनम्यूट होगा ना उसको
allow to talk now.
Yeah, Mr. Mohammad Hafiz Hassan, I think you are unmuted. You can speak now. Yeah, I think he's not there. Then
Yeah. So
then Mr. Sajid Kaji, allow to speak.
इसको बस वही allow to talk कर दो बस
हैंड किया हो ना उन्हीं को कर रहे हैं बस बाकी सबको नहीं कर रहे
नहीं ऊपर ऊपर वो बटन आता है सेपरेटली हाँ ये देखो ना allow to talk आया ना हाँ उसको कर दो बस
Yeah, Mr. Kaji, you are unmuted. You can unmute yourself and then speak. Okay, last one is Mr. Abdul Rahman Abdullahi. Oh, yes, okay. No, कोई नहीं.
Yeah. Okay. So thank you very much for raising many questions. We will also try to record, list out all the questions that have been raised, and also pass it on so that the further dialogues can take place. Yeah, Mr. Kazi, are you going to speak?
Yeah, are you hearing me?
Yes. Yeah. Go ahead.
The question is for the Dr. Philip, that how we manage the floods, how we can manage the floods in matured crop areas.
Thank you. I think it's a quite challenging question. And honestly, I don't have any magic trick. I think one of the key message that was coming from all the presentation is to have a better forecast. And of course, any tool or any method which is giving you the possibility to anticipate the situations that may happen and that may affect communities is relevant. So in some cases, it could be quite easy and simple to achieve, where you have quite easy weather condition you can forecast. In other situations, it could be much more challenging. Mountainous catchments are much more challenging. In both cases, so it means we have to multiply observation, monitoring of the weather condition, and try to have efficient models that could provide at the right scale information for having the right decision process taking place afterwards. One of the key difficulty is to address small catchments, obviously. When you have large entities, this is what our colleague from Thailand was presenting, you can succeed to have a good idea about the processes. But of course, when you are looking to very sudden and very extreme rainfall events that can take place over small surfaces, the challenges is much more higher. So this is something which is well known in Japan. And this is where we need to combine different type of solution all together to provide an efficient answer. I do not know if it's totally answering to your question, but the answer is not one single solution, but several solutions altogether on the forecast and also on the mitigation actions.
No.
Yeah.
Thank you. Thank you.
Thank you, Professor
Thank
Philip. And now I would request Dr. Kamran Imami, Vice President Honorary and Chair Working Group at Deputy Flood Management, to give his closing remarks. Yeah, I think we are not able to connect to Dr. Kamran Imami. I'll close the webinar on his behalf. We are indeed grateful to all the presenters who made very valuable presentations and provided an extremely good insight into the flood forecasting and also the inundation modeling. These are very great challenges to the humankind, and we are still struggling with it. There are various models available, but then the adjusting the parameters of the model is a very big challenge, especially even in the neural networks based approach. Also, the issues that remain are that when we prove the model against the one flood, but then the next flood that may be coming will be having a completely different kind of characteristics, and then again we have to see that how the model can perform in this. So we have to have a kind of a great number of ensembles of models, and then find the right solution out of them. Simultaneously having the strong field observations and field correlation is a very important aspect of any kind of forecasting, and that is used successfully in number of places based on the experiences. As the climate changes and as the floods and the rainfall intensities change, it will be always an effort to remain relevant in the areas of forecasting, and also forecasting in a manner that the properties and the lives are saved to the maximum extent possible. So I am highly thankful to all the participants. We had at the peak of the participation, we had almost 163 participants, which is a very encouraging figure for all of us. And we believe that we will have more and more discussions on this vital aspect during the future periods. And we'll be happy to have more webinars and more presentations on these aspects. So thank you very much to everybody and all the presenters and all the interveners. And we wish that we will be able to progress further on this aspect. Thank you very much.